Hi, it's Terry Denery of the MathWorks. So let's get into this whole field-oriented control thing, right? And so we're going to look at this example that we used in our previous video. And so it's an electric motor that is going to be delivered voltages in a way that it goes from non-movement, zero velocity, up to 10 rotations per second. Okay, and it does this because field-oriented control works so well, and our results, you know, are shown to be so good here by the mere fact that the blue line is exactly on top of the yellow line. The yellow line is our command, and the blue is the response, and uh, they're almost indistinguishable. So that's great. So it's amazing how well this works. All right. So I want to jump into this thing we call the electric drive a little bit. And we'll see that there's our permanent magnet AC motor with its 3 electrical connections. And that here essentially is our algorithm. Right? And our algorithm's job is to deliver the voltages that will be put on the A, the B, and the C terminals. Right? And the way the algorithm works is mostly commanded by what we want to happen as expressed by the torque. So we got this shaft we want to spin, we deliver the right torque, and we know we can get it to move the way we want it to. And as a mechanical engineer, I love that. You know, mechanical engineers love torque. That's how we think. And our job quite often is let's figure out what the torque needs to be to really get the movement that I want. Okay, so anyways, I'm very kind of excited by that, you know, as I learn about field-oriented control, right? Now, with regard to the rest of the algorithm, well, it works based on observation or feedback, you know, and that we essentially feedback where's the shaft, and that will be the angle. And you'll see this kind of thing that might appear redundant, that we're also measuring or feeding back the angular velocity. And all I'll say that with regard to that is that sure enough, we could put in some numerical approximation and a derivative so that we never even need to think about it, that maybe as part of this, and we reduce the amount of feedback. I'll just say sometimes you want to be a little more intentional than that, and you give yourself more options. Okay, we might get into why this was important as we kind of move through this overall series. We may not talk about it again at all. Okay, but anyways. With regard to field-oriented control, it's based on the feedback of what's happening mechanically expressed by what the shaft is doing, but also what is it doing electrically. And here we'll see feedback on the currents, the A, the B, and the C current. So it's a 3-component signal that expresses the currents that are flowing through the A, the B, and the C circuitry of the permanent magnet AC motor. And now I just want to jump in here very quickly and kind of get into what's happening here. And I think I'll just kind of point out maybe one of these MATLAB functions. First of all, I want to say I love MATLAB functions because it's all about MATLAB, and MATLAB's a great way for me to programmatically kind of express what I want to occur mathematically. And part of why I love MATLAB is it does things like expresses things in vectors. And we'll see as we kind of move through this that vectors are very important to, I'll at least call the implementation of the idea of field-oriented control. So anyways, let's get into field-oriented control. And so here are my PowerPoint slides, and I think I'll begin with this one. All right, so this representation of essentially 3 coils, 120 degrees separating each of them, if you kind of go through the rotation, is about as simple as it can get for what a 3-phase AC motor would be. Okay, it basically would say that I apply voltage, I apply voltage on a set of windings that I've called A. I apply a different voltage on a set of windings I call B, and I apply voltage on a set of windings that I call C, right? And what I want to kind of get at is that you apply voltage and you drive current through these coils, and essentially you generate a magnetic field, and that magnetic field will be proportional to the amount of current that's passing through it. Okay, and so there's this idea that there's orientation, you know, that magnetic field will be oriented as is the way out of those coils, as well as the case for the B and the C, of course. All right, and so this idea that something has orientation or direction, but also has amplitude, well, that very much is kind of expressed very effectively by by vectors. And so as I kind of discovered this about field-oriented control, that they're using vectors to really as the foundation of really kind of the derivation of how all this works, I got excited. So I'm a mechanical engineer. I love torque. I also love vectors. Everything that we do, is about kind of what are forces and torques and acceleration and velocity responses to such things, angular momentum. Every one of these concepts is expressed as a vector, okay? And so anyways, we're going to see vectors are really important, and we'll kind of get into that as we kind of go through the mathematics of this. Now, right before we kind of jump into that, I do want to bring up a picture of a real motor. So generally, motors don't have just one winding for each of the A, the B, and the C directions. It usually looks a little bit more like this. Right? And so this real motor probably is representative, at least with the number of coils, of probably like 99% of every permanent magnet AC motor I've ever worked with. Okay. And so what I want to just kind of point out is that there might be 12 electromagnets, but there's still just 3 circuits, and that's why it's called a 3-phase motor. And it basically means if you were to sequentially go around and kind of look at each of these windings, you might say, well, that's A. Well, then the next one would be B, and then the next one would be C, and then you start all over again. It's A, B, and C again. And the reason it's got 12, well, there's this thing called pole pairs, and why they call it pole pairs, it's kind of beyond me why they would call it that, but I'll at least say it's kind of a funny name for me for what it is. But let me just say that the number of windings will be the number of pole pairs times the 3 phases of A, B, and C. All right. And so with regard to kind of moving into this vector mathematics, I do want to emphasize the point that what we're doing now applies equally well, and maybe even more. It's even more effective when you consider 12, okay? Because each of those 12 windings, they are going to have their own individual orientation, and therefore their the reduction that we're about to observe as we kind of show that 3 can be reduced to 2, while 12 can be reduced to 2. So the efficiency of kind of reducing things through vector math is even more strong when you use real motors with additional pole pairs, right? But the basic idea is that you want to wind things up in an X and Y direction, Y, X, and Y, okay? Well, here's where with regard to vectors, the electrical engineers got a little bit easier than the mechanical engineers. Now, when you talk to a mechanical engineer and you're trying to understand how the mechanics of a system work, they start doing this a lot to you, okay? And what they're really doing is they're going, oh, that's a Cartesian coordinate system. And it's like X, Y, and Z, and so as you work in 3 dimensions, you have to have all 3 to kind of get there and define orientation and angles and all the things that you'll need to do. All right, and it gets a lot more complicated in 3 dimensions than it does in 2. But with regard to a motor, that rotor is turning in a plane, and therefore there is no third. It's really all about X and Y. Okay, and in general with a motor, what you do is a 3-phase motor. You take one of your A magnets and you say that's my x-axis, and then your y is just naturally perpendicular. But what you really do is each of those electromagnets, you essentially project them onto the x and y frame, okay? And so for example, B, here's a projection on y, and here's a projection on x, and you just add all this up, and you essentially come up with a reduction that effectively kind of is represented by this. It's the idea that, okay, instead of 3 electromagnets, well, you kind of have this thing that we call equivalent. And it's that you could replace those 3 electromagnets, at least for this instant in time that we want to look at, by these 2, and mathematically, you would essentially have the same thing. And so I found that electrical engineers, they love this term equivalent and equivalence, and it's ultimately beautiful for us because it is going to lead to this efficiency that's going to enable us to come up with an algorithm that will work really well on embedded processors and make motors do what we want them to do. Okay, so anyways, this idea of taking 3 or 12 and reducing it to 2, this is what they call the Clark transform, right? And it's a projection of all those vectors onto a stationary XY plane. Okay. All right, so then this guy Park, and it's really kind of funny that he's got a name that rhymes with Clark, and it's a little confusing, but it is kind of cute. And it's the Park and the Clark, and the Clark and Park transforms are very critical to how this works. But what they came up with next is this beautiful kind of recognition that, okay, it's not only good to reduce everything down to the equivalence of two electromagnets, if we could put it on a reference frame that rotates with the rotor, that's really valuable, right? And not only that, if we can line it up so that one of the axes is lined up with the north-south polarity of the rotor, that's even better, okay? And so anyways, we go from X and Y to what they call the D and the Q axes. And so D and Q, they spin with the rotor, right? And so anyways, the other thing that they kind of came up with, which was so beautiful, was kind of recognizing the concept of an electromagnet, that there's this idea of inducing a magnetic field, so we'll call that induction, and there's also this idea of generating a torque, right? And this is all about kind of having the magnetic field of the stator created to interface with the rotor to do these things. But this idea, of induction and torque generation, kind of it came to make sense to me as I recalled my fifth grade science class. I remember, getting this copper wire, and the copper wire had insulation on it, and so I'd wind it around this nail, and then I'd take a battery and I'd connect the two loose ends of the wire, and I created essentially an electromagnet. I essentially induced the magnetic field. And so anyways, let's do one more quick. And so the Park transform is really about kind of now coming up with, this again, a somewhat a mathematical construct that we're kind of imagining that there are electromagnets on these D and Q axes, right? And so if I'm driving current about the D electromagnet, I'm inducing a magnetic field that happens to be superimposed on the natural north-south axis of the rotor. It means that if I drive current through this kind of mathematical construct of a D, electromagnet, that I'm going to either add to the magnetic field of the rotor, or I'm going to reduce it, depending on whether I'm sending positive or negative current through it. Right? Okay. Turns out if you have a permanent magnet AC motor, typically you want to drive zero and just let the natural magnetic field of the permanent magnet, handle that piece for the rotor, right? So then what I thought was really amazing is that these predecessors to us, and I guess Park and Clark were two of them, but I'm sure that Tesla was very well informed on this idea too, of the importance of D and Q. But this recognition that this perpendicular axis is entirely responsible for the torque that can be produced by an electric motor, and that even more importantly, that the torque that's generated by the motor, and that's based on kind of the windings and all that kind of stuff, but it's going to be proportional to the current that flows through this Q axis, right? And so with that, hopefully I gave a reasonable kind of introduction to field-oriented control. I would like to go back to the model now and just kind of show what's happening in the Clark transform. Essentially we're taking the currents in the A, the B, and the C circuits, and we're essentially returning alpha and beta currents. Now it turns out these are the XY currents for that stationary XY coordinate system. And you'll see that the math, and MATLAB, of course, is great at this kind of stuff, that we essentially establish these vectors. Again, it's a two-dimensional basis, so there's only a 1 and a 2 field for each of these, right? We multiply each of these unit vectors, which are really about the orientation of 0, 120, and 240, and we essentially establish a vector with an amplitude defined by the current for each. And so we got what they, it's kind of a crazy terminology, but what they call a current vector, right? And so then they just kind of add all these vectors, the way you add vectors, and then you essentially pick off the first component of the accumulated sum, and you say that that's I alpha, and you pick off the second one, that's I beta. There's a little bit of normalization. That's why you multiply it by 2 and divide by 3. Okay. Now, if you look at Park, it's really a lot simpler than that even. It's just a basic transform, delivered by kind of the right, I'll call it matrix composed of like cosine, sine, minus sine, cosine kind of stuff. Okay. But what's so empowering is it gets me to here. And here is essentially where my real control takes place, right? And so you'll see there's my torque command, all right? And here's my current expressed because I did the Park and Clark transform in terms of the DQ axes. And so the control is really taking place in this whole DQ kind of reference frame. And you'll see that the output of this whole thing is VDQ, right? And so, of course, controls is always about, well, what do I really physically have the ability to change? It's voltage, not current. The current is in response to what I'm doing on a voltage side. But if I'm very thoughtful about this and capture it properly in an algorithm, that I can get the currents I want, as commanded, and deliver essentially what really needs to be done, the voltages that will be applied. And so with regard to this, we do want our direct current to be 0. And so we set that right here, right? And I'll kind of explain why I'm having a 2-component right here that's essentially used by this term. Probably explain it in a separate video because it's really a very cool idea, but it would definitely take us another like 10-minute venture to really explain it. But I will just kind of point out, all right, that here are some PI loops. They're essentially employing feedback and driving our direct current to 0. And here's a PI loop on the quadrature, and you'll see that the quadrature is command on current is going to be fed by torque. We take torque, we multiply it by this gain that is composed of various things. They're very important about what the real motor is, and specifically we're seeing flex linkage and pole pairs, and I'll probably explain that as I kind of get into this piece in a future video. But that these are being combined with what I'm going to call my feed-forward controller to identify the best options on what I want the voltage on D and Q to be. Okay, and it's because I added this piece that I believe that we get this whole thing to work so well. And all I'll say with regard to the feed-forward idea that exists in this is that it is, again, taking what you know and understanding kind of these equations of voltage, these dynamic equations of voltage and current response that are expressed in this kind of DQ reference is used to, again, come up with a better understanding of how we want to vary our voltage, right? And with regard to, this outputting a VDQ, well, there is no D terminal, there is no Q terminal. This is a mathematical construct that allows me to be very efficient and very successful in getting a motor to do what I want it to do. But the reality, is that there's an A terminal, there's a B terminal, there's a C terminal. That's what I can put voltage on. And so the last piece of this is essentially unpacking DQ and going back to VABC. And I put every bit of it all into one MATLAB function. And in reality, what people would call this is the Clark, the inverse Clark, then multiplying into the inverse Park. Or is it the other way around? I think it's the other way around. But anyways, to get back to the real world, so that I can put voltages on real terminals, A, B, and C, it's necessary to do this final piece of mathematics, right? And so with that, I think I'll kind of wrap up. I think I got what I want, in this video now. And I just want to kind of point where we're going with this, right? And, I've emphasized again, the beauty of this for a mechanical engineer like myself, because we like operating with torque. And I told you how good we're at figuring out the right torque for the right mechanism to make it move the way we want it to. Well, that definitely deserves its own video, and we're going to get into that in the future. And in general, I'd say there's probably 3 trajectories that we're going to kind of pursue with a series of videos. And one will be understanding the mechanics and essentially figuring out things they call inverse kinematics and inverse dynamics so that we can kind of get the movement through the proper selection of torque to be delivered through a device like a permanent magnet AC motor. Okay, so we'll get into that, and we'll really kind of get into the mechanics and working with 3D shapes and the mass properties and all that. Okay, um, we'll get into the controls a little bit more deeply, and specifically, we'll kind of use what we know about the circuitry of the AC motor so that we can control that motor more properly with the appropriate voltages to get the currents that we want. Okay, and then finally, we'll kind of get into hardware implementation, hardware implementation of an algorithm. Okay, and this was really interesting as I started working with real, three-phase permanent magnet AC motors, and I started working with these hardware guys, and they really helped me, and it was kind of helped me see it from this extremely important perspective of someone trying to get something to work in the real world, right? And so specifically, they said something to me on the order of, well, us hardware guys, we don't really care about C. I'm like, what do you mean C? And they're like, well, there's the IA, the IB, and the IC. They're like, we don't care about C. And I go, yeah, and essentially, here's kind of their very efficient way of stating it is um, that why would I use 3 sensors when I can get away with 2? Okay, and so then all of a sudden I thought about it, all right, and all of a sudden it made sense to me. And what I recognized is, well, the A, the B, and the C circuitry, they're kind of grounded together. And what mathematical constraint that then imposes on the system is that essentially if you consider IA, IB, IC, that they can each be positive or negative, that they sum up to 0 always by this grounding, what they call Y configuration grounding. I think that's the term. But it means that if I know I and I know B, if I know IA and I know IB, I know C already. And so that was kind of interesting to learn. All right. But then the hardware folks, they also really impose this additional thing that's very important. And that this is an algorithm. And it's an algorithm that really kind of has the dynamics to it. And what I mean by that is that there is real mathematical calculus taking place. That there, and you see that in the PIDs. What does I stand? Well, it stands for integration. What's D stand? It stands for derivative. All right. And that dynamics always has to be approximated on a computer. Computers are about implementing discrete mathematics. And what that means is that the approximation includes this thing called a delta t, all right? And, we can definitely get into pretty heavy conversations about accuracy and stability and all that kind of stuff, but let's just say it as easily as we can. The things get better, the smaller delta t can be, okay? And so the hardware folks, they remind you that you have to live in the real world. And the delta T really does is the passing of time. And that the real constraint on how fast you can kind of update your mathematics, which is really represented by these feedback loops that exist in controls, that the real constraint is how fast can that algorithm, and actually I have a processor right here, this is an Arduino, might not be the one I'd use for an AC motor, but how fast can a calculation take place on that processor. And so if you can get this whole field-oriented control algorithm as compact and as efficient as possible, it means that you can run it at higher rates, all right? And so anyways, what I'll call it is the optimization of the calculation. And as we move to hardware, it'll be various things. One will be the accommodation of the real hardware, which might be that there's only an A and a B current sensor, but there will also be this major focus to make that calculation take place as fast as possible. So anyways, I'm looking forward to recording these upcoming videos, and thank you very much for attending this one.